Picture this. You're sitting in your living room holding a coin. You flip it in the air and wait for it to land. In everyday life, you know what happens. It will come down either heads or tails, one clear result, no mystery. But in the bizarre world of quantum mechanics, the rules are very different. If that coin were small enough, say the size of an electron, it wouldn't just land heads or tails. It would exist in a strange limbo where it's both heads and tails at the same time until you look at it. And the moment you look, the act of looking itself decides what it becomes. That's the kind of unsettling logic that governs the smallest building blocks of the universe. Quantum mechanics isn't science fiction. It's the foundation of modern physics and the reason we have technologies like semiconductors, lasers, and the beginnings of quantum computers. But as powerful as it is, quantum mechanics also confronts us with paradoxes, puzzles so strange they defy common sense. These paradoxes don't just make us scratch our heads, they make us question the very nature of reality, of time, of consciousness, and of the universe itself. Does the universe exist when we're not looking at it? Can watching something literally freeze it in place? Are there infinite versions of you spread across countless universes? In this video, we'll explore the top 5 quantum paradoxes that will melt your brain, explained in detail with easy-to-understand examples and the latest updates from modern science. By the end, you may not see reality the same way ever again. And if this is your first time here on beyondx, don't forget to subscribe so you won't miss our upcoming mind-blowing videos. And of course, feel free to share your thoughts in the comments below. The first paradox is about Schrödinger's cat, when the state's alive, dead, and both coexist. This is one of the most famous paradoxes in quantum mechanics, comes from Erwin Schrödinger, who in 1935 came up with a thought experiment that still shocks people today. He wanted to show just how bizarre quantum theory sounds when applied to everyday objects. Imagine placing a cat inside a sealed box with a tiny amount of radioactive material, a Geiger counter, a vial of poison, and a hammer. If the radioactive atom decays within an hour, the Geiger counter detects it, triggers the hammer, breaks the vial, and releases the poison, killing the cat. If the atom doesn't decay, the cat lives. Now, according to quantum mechanics, before you open the box, the atom is in a superposition. It has both decayed and not decayed. This means the cat is both alive and dead at the same time. Only when you open the box and observe it does the cat choose one outcome, alive or dead. This paradox captures the idea of superposition, where particles exist in multiple states simultaneously until observed. That sounds insane, but experiments prove it's real. Electrons can spin both clockwise and counterclockwise at the same time. Photons can pass through 2 slits at once, interfering with themselves. In 2019, scientists pushed this further by putting massive molecules, containing over 2,000 atoms, into superposition. The idea that something so large can be in multiple states at once gets uncomfortably close to our macroscopic world. To understand it in everyday terms, think of milk in your fridge. Normally, it's either fresh or spoiled. But in quantum mechanics, until you open the fridge, the milk is both fresh and spoiled simultaneously, existing in 2 possible realities. The paradox raises the measurement problem. What exactly causes the collapse from many possibilities into one reality? Does it require a human observer? Can a camera do it? Or is the universe itself constantly measuring itself? Some interpretations even suggest consciousness plays a role in defining reality. Schrödinger's cat isn't really about cats. It's about whether reality is objective or whether it needs us to exist. The second paradox is about the observer effect. Does reality exist without us? The observer effect is the strange idea that simply observing something changes its behavior. The most dramatic demonstration comes from the double-slit experiment, first done over 200 years ago but still shocking today. It was the double-slit experiment, first performed in 1804 by Thomas Young. Here's how it works. Scientists fire particles, like electrons or photons, at a barrier with 2 slits, with a screen behind it. If no one checks which slit the particles pass through, they behave like waves, going through both slits at once and creating an interference pattern on the screen, like ripples overlapping in water. But if scientists measure which slit the particles go through, the interference pattern disappears, and the particles behave like solid bullets, going through one slit or the other. It's as if the particles know they are being observed, and they change their behavior accordingly. This paradox raises one of the most unsettling questions in all of science. Does reality exist when we're not looking at it? Imagine baking cookies. If no one is in the kitchen, the dough mysteriously spreads into multiple trays at once. But the moment you peek, the dough instantly snaps into just one tray. That's the double-slit experiment in simple terms. Scientists argue about whether human consciousness is necessary for this effect or whether it's just the act of measurement itself. But either way, it suggests that observation plays an active role in shaping reality. In 2023, researchers using quantum computers simulated the act of measurement and suggested that information, not matter, may be the true foundation of existence. If that's true, then the universe is less like a solid machine and more like a giant cosmic computer that only renders reality when needed, like a video game generating graphics only when the player looks at them. This makes us wonder, are we discovering the truth about the universe? Or is the universe revealing itself only because we're here to look? The third paradox is about quantum entanglement, the invisible cosmic thread. Einstein despised this paradox, calling it spooky action at a distance. Quantum entanglement happens when two particles interact and become linked so that their states are correlated no matter how far apart they are. If you measure one particle, the other instantly knows and takes on the opposite state, even if they're light years apart. This appears to violate the speed of light, since the effect is instantaneous. For decades, scientists argued whether this was real or just a flaw in quantum mechanics. But in 2022, the Nobel Prize in Physics was awarded to scientists who proved entanglement beyond doubt. And in 2024, experiments using satellites managed to entangle photons across distances of more than 1,200 kilometers, confirming the reality of this instantaneous connection. Imagine you and your best friend each own a pair of magic dice. You live in New York and your friend lives in Tokyo. Whenever you roll your die, your friend's die instantly shows the same number, no matter the distance. That's entanglement in everyday language. This suggests that the universe is not local, meaning that parts of it are connected in ways that transcend space and time. Some scientists even speculate entanglement might explain consciousness or mysterious connections in the universe that we can't yet see. And it's not just philosophical, it's practical. Quantum entanglement is now being used to develop quantum cryptography and the quantum internet, systems that could revolutionize communication by making it impossible to hack. But the paradox remains, how can particles separated by vast distances act as if they're one? Does this mean there's a hidden layer of reality that ties everything together like an invisible cosmic web? Entanglement hints that the universe might be more like a single unified whole than a collection of separate parts. The fourth paradox is the Quantum Zeno theory, watching freezes time. Named after the ancient Greek philosopher Zeno, who famously argued that motion was an illusion, the Quantum Zeno paradox suggests that constantly observing a system can stop it from changing. Quantum mechanics predicts that if you measure an unstable particle often enough, you can prevent it from decaying. This was experimentally confirmed in 2015 when scientists trapped atoms and used lasers to watch them continuously. The atoms stayed frozen in their states, refusing to evolve. In other words, observation literally stopped time for those particles. Imagine boiling a pot of water. Normally, the water heats up and eventually boils. But if you lifted the lid and checked every single second, quantum mechanics suggests the water might never boil. That's how strange this effect is. In 2024, quantum engineers used this principle to stabilize quantum bits, fragile pieces of information in quantum computers that normally collapse almost instantly. Thanks to the Zeno effect, these quantum states can be preserved long enough to perform real computations. The implications are staggering. If observation can stop decay on the quantum level, could it be applied to larger systems? Could it prevent biological decay, aging, or even death? That's still speculation, but the paradox shows that observation doesn't just reveal reality, it can shape it, even control the flow of time itself. This makes us ask, what is time really? And if simply looking at something can freeze it in place, are we underestimating the role of consciousness in the unfolding of reality? The final paradox is perhaps the most mind-bending of them all, the many worlds interpretation. Proposed in 1957 by physicist Hugh Everett, it suggests that every time a quantum event occurs, reality splits into multiple universes. If you flip a coin, in one universe it lands heads, in another it lands tails, and both universes are equally real. That means there are infinite versions of you living out every possible scenario. Imagine standing at a crossroads. In one universe, you choose the left path. In another, you choose the right. Both are real, and both versions of you continue to exist. In 2024, quantum computer simulations suggested that the many worlds interpretation could resolve paradoxes like Schrödinger's cat without needing observation to collapse possibilities, because all possibilities happen just in separate branches of reality. This is terrifying because it means there may be no such thing as a single, definite outcome. Every choice, every possibility plays out somewhere. The paradox raises deep questions. Which version of you is the real you? Do you live only in one branch, or do you somehow exist in all of them? Some philosophers argue that consciousness may ride one branch, while others suggest we might exist simultaneously across them all. The many worlds theory also fascinates people because it could explain phenomena like the Mandela effect, cases where large groups of people misremember reality, such as believing Nelson Mandela died in prison when he did not. Some speculate these are glimpses of alternate universes overlapping with ours. Whether or not that's true, the many worlds paradox forces us to accept that reality might be endlessly branching, and that the universe is far stranger than we can ever imagine. These 5 paradoxes, Schrödinger's cat, the observer effect, quantum entanglement, the quantum Zeno effect, and the many worlds interpretation, aren't just abstract puzzles. They are cracks in the foundation of reality itself. They show us a universe where particles can be alive and dead at the same time, where observation shapes existence, where distant objects are mysteriously connected, where watching can freeze time, and where every choice may spawn infinite versions of reality. Quantum mechanics has already transformed our lives through technologies like semiconductors and lasers, and it promises to transform them again with quantum computers and quantum communication. But beyond technology, these paradoxes force us to confront deeper questions about existence, consciousness, and truth itself. What is reality? What role do we play in it? And can science ever fully capture the essence of the universe? The more we learn, the more uncertain everything becomes. And maybe that's the real paradox. Certainty is an illusion, and the universe is far stranger than we can comprehend. Thanks for watching. If this journey through quantum paradoxes melted your brain, but also ignited your curiosity, don't forget to like, subscribe, and hit the notification bell to support beyondx. The universe is stranger than science fiction, and we're only beginning to scratch the surface of its mysteries.